Hi, welcome to In 5 Minutes. We have seen the construction and working of E-MOSFET. Now coming to the different biasing types in the E-MOSFET as we have seen in the BJT also. Now coming to the different types of bias. We can identify the MOSFET. Since you have the three separate lines, it indicates that it is a E-type MOSFET. Now depending on the arrow, it is inside, so we can say it is an E-MOSFET. Now feedback biasing is part of the output is fed back to the input, so this type of biasing is called as feedback biasing. Now what you can see in the diagram, the resistor RG brings a suitably large voltage to the gate to drive the MOSFET on, but we can say the current flowing into the gate IG is 0. So we can say since IG equals to 0, voltage drop across RG will be 0. That means we can neglect RG from the circuit. So how the circuit will look like after neglecting RG is like this. We are removing the effect of RG. So what we can say from the diagram, since drain and gate are the same point now, so we can say VD equals to VG, that is the voltage at the drain equals to the voltage at the gate, or we can say VDS, that is drain to source voltage, equals to VGS. Since drain and gate are same, so we can simply tell like this. Now when you apply KVL at the output, you can say KVL to output. So what will be the equation? VDD, current flowing to RD is ID, so minus ID into RD minus VDS, we are living with a negative sign, so minus VDS equals to 0. So what we can say, VDS is equals to VDD minus ID into RS, right? So this we got the relation. So if I substitute 1 into, what I will get? I will get VGS equals to VDD minus ID into RS. So this equation I got, I call it as equation number 3. In this equation, if I substitute my value of ID to be 0, if I am substituting ID is equal to 0 in equation 3, what I will get? VGS will be my value of VDD, and in the same equation, if I substitute VGS equals to 0 in equation 3, what I will have? I will have VDD equals to ID into RD, or I can say ID is equal to VDD upon RD. The same thing we have done for plotting the load line in case of the BJT. So in this case I can say my VGS is 0, and in this case my ID equals to 0. So I have got 2 points. So when plotting on the graph, you can say when your ID on y-axis you have the current, x-axis you have the voltage. When my VGS is 0, I will have ID as the maximum value, which is VDD by RD. When my ID is 0, that is on this axis, my maximum value will be VDD. So when I join this, I will get the load line in this case. So this is how you can draw the characteristics. As I have told you, this is the maximum point, VDD by RD. The value is ID max, you can say, and this is nothing but your VGS max. When your ID is 0, VGS is maximum when your ID is 0, and ID is maximum when your VGS is 0. The graph, when it is intersecting with the transfer characteristics, the point what you get is the Q point, and the coordinates will be the IDQ for the current and VGSQ for the voltage. So x axis you have VGSQ and y axis you have IDQ. So while writing, we can write Q point as VGSQ versus IDQ. Right, so this is how you can get the Q point. Now coming to the problem based on the fixed bias, say there is a problem to find IDQ VGSQ for the given MOSFET. You can say the symbol is same what we have done the analysis, so immediately based on this same concept we can solve the problem. So we can say for the transfer characteristics we require the value of K. We can find the value of K, as you know, it is ID on upon VGS on minus VGS threshold the whole square. So VGS threshold is nothing but your VTN. So what is given? VTN is given as 3 volts VGS on is given as 8 volts and ID is given as 6 milliamperes. So when you substitute these values, you will get K as 0.24 into 10 raised to minus 3 ampere per volt square. So we got the value of K.